No matter what theta you ever plug in, you're always getting 5. This is like in Cartesian if I ask you to graph x equals 4. X equals 4 will be a vertical line because no matter what y you plug in, your x is always 4, right? So if I write r equals 5, here the radius is 5 regardless of the angle you're given. So this should draw me a circle of radius 5, right? Now, in Cartesian, if I write y equals 5, let's say, now you're drawing a horizontal line, right? Because your y is 5. It's completely independent of what the x value is. So let me do the same thing in polar. If I write theta equals, I don't know, pi over 2. That just says aim at pi over 2 and walk out how far? Continuous, like whatever I want, right? R can be anything you want. So what is this actually drawing?
A line at pi over 2.
A line. It's y equals x. This is y equals x. Oh, wait, hold on. Sorry. I thought I put pi over 4. Let me put pi over 4. I wanted pi over 4. My bad. Pi over 4. You aim at pi over 4. All this says is, look, aim at pi over 4. Right? Like that. And then as far as the radius, it's a free variable here. You can walk out 0, you can walk out 1, walk out 2, walk out -1, and it has no impact on this, right? It's kind of interesting, right? Like in Cartesian, when we say x is a constant, you get straight line, right? You say y is a constant, you get straight line. In polar, you do r as a constant, you get a circle. You do theta as a constant, you get a line, right? Change your angle, it's just going to rotate this line. All right, let's now do a problem. This is similar to a problem on your next mini exam. And I handed those out last time, right? Yes. Okay. If anyone needs one, I think I have some extra copies. I think it says it on there. I don't remember. 10 sounds good to me. 2 weeks from today? Yeah. A sphere of radius 3, has a cylinder of radius 1 drilled out of it as shown below. Set up the double integral which yields the volume of the remaining solid. Do not evaluate. So I showed you all this at the end of class last time. Here's your sphere of radius 3. Actually, that looks like it has a radius of 4, doesn't it? That's just a typo in my code. Just ignore that. It's supposed to be 3, okay? And I want to drill out along the z-axis, right? I'm going to run my drill bit so that it is running kind of tangent to the z-axis. I'm going to drill out that part of that sphere, and I want to know what the volume is that remains, all right? What volume remains? So I think logically what we could do is we could say, take the sphere and find its volume, right? Without drilling anything out of it. And then subtract from that the volume of the piece that you drill out, right? The piece that you take out, let's just subtract that from the volume of the whole thing. Now the piece that I take out, that I drill out, is not a true cylinder. Like, see the green right there? That's a cylinder. The part I take out is not a true cylinder. I'm trying to show it to you. I'm going to take the cylinder out of here. The part we're drilling out, right there, that part that we drill out, when you look at it from the top and kind of zoom in on this, right? We have a little curve up there at the top, don't we? It's not flat like a true cylinder. And so we can't just use the volume of a cylinder to figure out what that volume is. What we can do, though, is just try and look at maybe finding the volume of that piece, just half of it, just the top half of the part we're going to drill out, because the symmetry, right, of the top and bottom. If we just look at the volume, trying to find the volume of that piece, then see if I bring the sphere. That doesn't help. If we try and find the volume of that piece, whatever that is in red there, has a little bit of a curve to it here. You know, it's got a little bubble on the top. If I take away 2 of those, then that should be my volume, right? Agreed? You understand my plan? Okay, let's start with this one. What is the volume of the sphere? Well, that we're just going to resort to the formula. We know the volume of a sphere is 4/3 pi r cubed. 4/3 pi r cubed. So starting with that first picture here, yeah, so the volume of this, the volume we're looking for is the volume of the sphere minus the volume of the drilled out part. I'm just going to put volume of the drilled, all right? Let's do the, do you want me to put the 2 here? No, I'm just going to leave it as drilled. The volume of the sphere is 4/3 pi times the radius cubed. That's a formula, so the radius of that, I said was 3, right? I said that sphere had a radius of 3? So I'm going to put 3 here. Okay, that's a number. That's easy. No problem. We can figure out what that is. Minus the volume of the drilled. So let's focus our attention on trying to figure out what the volume of that drilled piece is. So do you all see that this drilled out piece has a top surface? Which is the what?
The sphere.
Sphere. And then the bottom is the XY plane, right? And do you see the domain on the ground, what we're actually integrating over?
Yep.
Circle, right?
Isn't it all 2 cosine theta?
Yeah, it's the example we just did. But I'm gonna illustrate this with, we're gonna look at it from the top like that, right? Did I stress that this had a, yeah, the drill bit had a radius of 1, right? All right, so let's do this. So in terms of my domain, my R, my region on the ground, I have this picture. Now, I could orient this drilled out piece, I could orient it any way I want, right? If I wanted to, I just got to make sure it runs tangent to the z-axis going into the board, right? My z is like this. I could put it anywhere I want as long as it's running like my drill bit is parallel to the z the whole time, right? You understand? I can position that circle anywhere. But it just makes sense to make it nice and oriented so that the center of the circle lands on one of these axes. I think the one that makes most sense is the one we just did, which is to put it on our x-axis like this. And it has a radius of 1, which means that the center of it is 1, right? It's got to be 1 this way, 1 this way, 1 up, 1 down. So had we not done the problem we did just before this, right? Had we not done that, we would have no idea what that is as a polar region. It's not a polar rectangle though, right? This is not a polar rectangle. This is, what? What is the equation of this? R equals cosine theta, right? R equals cosine theta. That's what draws that. Two cosine theta. I keep leaving that 2 out. Jeez. Trying to think of what order I want it. Let's do R first. Let's do R in terms of, we could set up the integral, but let's do the region first. I need to get my theta between 2 constants and my R between 2 functions of theta. So what do we have in terms of theta? We hadn't really gotten to this in too much detail, but in order to draw this region here, my theta is going to have to be between where and where. Let's see. Well, if I start at 0 and go this way, right, it's going to draw, what did we say? At 0 it was there, but then at pi over 2 it was there. So if I go from 0 to pi over 2, it only draws me the top half, right? I want the bottom half as well. So we have 2 options. We can keep going, because remember when we went over here, it drew it backwards, right? Or we could, instead of looking at it between 0 and pi over 2, we could go from negative pi over 2 to pi over 2. It's really up to us. So you want to go negative pi over 2 to pi over 2? Yeah? Negative pi over 2 to pi over 2. That should draw it. Now, again, just to show with technology, we should be able to verify that. See how it gives me a restriction here on theta? I can restrict it. If I do 0, let's go to pi, let me go pi over 4, and it's just going to draw me that one little piece, see? If I want to check and go pi over 2, that's going to draw me the top half. Let me go to pi. If I go to pi, it should draw the whole thing, right? So I could have gone from 0 to pi, or I could have gone negative pi over 2 to pi over 2. What you don't want to do is go 0 to 2 pi, because what would happen if you go 0 to 2 pi? It draws it twice. So that would be incorrect, because then now you're like you're getting twice as much. All right? Yes?
Can we also apply like symmetry and go from 0 to 2 pi, but just multiply the interval by 2? Or does that not work in this case?
Great question. So the question was, could we just go from 0 to pi over 2 and double it because of symmetry? Yes or no? What do y'all think? It depends on what the surface above it looks like. Is it symmetric up there? So you're saying let's only do this part and then go up through the surface there, right? Is it symmetric? Is this solid above this symmetric to the solid below it? See, we could argue. This is why it would be dangerous, right? It actually is, but are you convinced that it is? I mean, you have to look at the picture.
I think at least like it has to be centered on one of the axes.
It would have to be centered on one of the axes for that to work. So if I look at it from this angle right here and look at it kind of like that, you can see that this side over here is completely symmetric to that side. Now, if I rotate it the other way like this and look at it, see this way, you don't have symmetry that way, do you? Right? So you always have to be careful with the surface on top, because if it's not symmetric up there, you can't just double it. Good question. All right. Let me see. I think that's it with that part. In hindsight, I kind of wish it was 0 and pi, only because those are easier numbers to plug in for me, but I can deal with that. All right, R. What's my restriction on R? So this is, 0 to 2 cosine theta. So I want us to really consider this, why it's so important to understand this inequality. 0 to 2 cosine theta. This draws the ring, right? The circle. But the inequality says, okay, give me a theta. Like, let's say theta is 0. Then if theta is 0, this is 2, right? And that means I want to go and walk out how far? Between 0 and 2. So that means when theta is 0, I'm going to walk out between 0 and 2, and that will fill that in, right? If I rotate a little bit, then I go from 0 to whatever that value is, like square root of 2. Like when we went 45 degrees, I'd go 0 to root 2, and I would draw everything in between. And if I did that for all of them, all the angles, I'd start filling in all of these like this. And eventually, I'd fill up that top half, and then if I went the other way, then I'd fill in the bottom half. So it's like I'm drawing it, that's the way I'm drawing the region. So now we set up the double integral. Well, we haven't gotten our top surface and bottom surface. So what was on our picture, this top surface was our f of xy, which was the sphere of radius 1, which we could solve for z and get that same thing we had earlier. Oh wait, no, what is our radius? Sorry. Radius is 3. So this would be 9 minus x squared minus y squared. I was confusing it with the previous problem, right? And then our g, which is the bottom, g of xy in this case, is just the xy plane, or z equals 0, right? Just the ground. We've got to convert both of those to polar. And then once we convert them to polar, we put the integral together and we integrate, right? Now, do y'all remember when we were doing type 1 with Cartesian, you are no longer free to flip the order of integration. You actually now have to go in the proper order. And the outer integral will always be the one that has the variable where you're in between constants. So for us, the outer integral is going to have to be with respect to theta. So the volume of the drilled part will be equal to double the double integral negative pi over 2 to pi over 2. Why did I put that 2 out front again? Why did I do this out front? We're only doing the top half that we drilled out. I'm putting the 2 in now to account for the bottom half that is symmetric. And then, all right, we're going to do this minus this. Well, this doesn't even matter. It's 0, right? So that is just the square root of 9 minus, I'm going to polar. Same thing we had earlier. That's just r squared, isn't it? Minus r squared. Factor out the negative. Then it becomes x squared plus y squared. Convert that to r squared. And then we have r, because we converted to polar. That's that important r that you have to insert. That comes from the Jacobian determinant that we'll talk about later. Then dr, then d theta. Oh, I forgot to put my limits here. 0 to 2 cosine theta. There it is. And then we go from there. Yes?
Why is g of x and y 0 again?
Well, we decided when we were looking at this picture, we decided that instead of trying to find the volume of the whole thing,
Yeah, we're doing half.
we're doing half. So I put a 2 in front just to double that red, right? So that's not what you're asking me. You're asking me why is g of x 0? Because if I do this half, then the ground, the xy plane, right? The xy plane is the bottom of this thing.
Okay.
So that's why I put g of xy 0. I could have, if I wanted to, not use the 2, but then I would have had to have changed g of xy to that surface, but negative. So this would have had to have been negative square root of 9 minus x squared minus y squared. And then I could do it as without having to double the answer. But that is an uglier integral. Yes?
Finding the volume of the drilled part, why are we using the radius of the sphere instead of the radius of the cylinder? Or the radius of
Got you. Okay. The great question. The question was, why am I using 9 here and not 1? Because the cylinder has a radius of 1, right? The reason is because all I'm trying to do is figure out what is the surface on top that is controlling that drilled out part, right? So what is actually the boundary? What is that boundary surface? Where does it come from? Is it the cylinder or is it the sphere? It's the sphere itself, right? The sphere is what actually caps off this piece, right? The sphere does. So the top surface, right, is that function. Now, where is the 1 coming from? Like, then where is the 1, right? It's the 1 is taken care of with this polar region. That's where the radius 1 is actually accounted for. It's in your limits of integration. This is going to draw you a circle of radius 1. Good? Good question. Good question. Anything else? I said set it up, but not evaluate it. Do you think you could do the inner integral pretty okay? Basic U sub?
Yeah.
That's a basic U sub, right? And then after that, you plug other things in. I went ahead and had the computer do it for us. And what the heck? Oh, okay, so what did I do? I don't even know what I did. So this is it right here. If you do that double, I went 0 to pi on the computer. See that? 0 to pi. If you do that, then you should get 17.1639. And then I had the computer do 36 pi, and then I'm not sure what I did here. Oh, I just put them together. I took that integral we just did, and I subtracted it from the 4/3 pi r cubed, and I get a final answer of 95.9334, approximately. Or you could say, if you wanted to know, how much did you drill out, right? If you do that, how much did you drill out? You could just say it's 17.1, whatever, cubic inches, cubic meters, whatever your units are. At the end of class last time, we proved that the area of a circle was pi r squared, right? We just used this formula, right? We just used it, and we just trusted that it was correct, right? But can we prove that the volume of a sphere is 4/3 pi r cubed? We've been using that formula in our lives, right, in different places, but now let's actually show that that's what it is. There's a couple of ways to go about this. I think the easiest way is to just start with a sphere. Ooh, that's a good sphere. Okay, let's start with a sphere of radius capital R. All right, that's a sphere of capital radius R. I want to prove that that has a volume of 4/3 pi r cubed. So how about this? I like this attack here. Why don't we find the volume of just the top half of it and double the answer? Just the top half, double the answer? Yeah. So if I take just the top half, still has a radius of capital R, then I just need to know what's the top of this surface, right? What's the top surface, what's the bottom surface, and then what's the region that we're integrating over. So what's the top surface? Well, it's a sphere of radius capital R, right? So the equation for that is x squared plus y squared plus z squared equals r squared, capital R squared. And if I solve for z, then I get the square root of capital R squared minus x squared minus y squared. Y'all following? Capital R is the radius of this sphere. It's fixed. The capital R is a constant, right? It's a constant in the problem. That would be my top surface, right? I call that the f of xy. Then what's the bottom? 0. Again, because it's convenient to just do the top half and double the answer, right? So g of xy is 0. And then let's go look at the region on the ground. This is our region on the ground. It's the actual, it's just a circle of, or a disk, I should say, a disk of radius capital R, isn't it? Because we cut it right in half. We oriented everything at the origin, just cut it right in half. And that is that region in here. I'm using capital R in two different places to mean two different things, but I hope you understand. We're talking about the region capital R, and here I'm talking about the capital R of the radius of the sphere. That's a polar rectangle, isn't it? You don't need anything fancy here. This is just theta's between 0 and 2 pi. That'll draw that. As long as our radius, little r, is between 0 and capital R. I'm going to take just a real quick side thing here. Raise your hand if you want to try and answer this. Don't just blurt it out. What if I wanted to draw that same circle, radius r, but I forced you to only fix your theta between 0 and pi? Then what would your radius, how would you then control your radius? Could you do it? Could you draw that? And I should say it this way. Could you draw that disk, everything in here? Could you draw everything in here by just going between 0 and pi? Go ahead. Negative r to r? What do y'all think? That's what you say? Negative r to r? Think about what that means. If I go negative r, well, let's do it right now, just 0 to r. What would that draw? That would only draw that top half, right? Because you would go and you say, okay, at angle 0, I go from 0 to r. Then angle, like let's say pi over 4, I only go from 0 to r. Everything in between, you draw it like this, right? So it's kind of like you're drawing like here, and then here, and here, and here, and here, and here, and here, and here. And you go halfway around. The suggestion is that we change this to negative r. And now, when you're aiming out this way, right, at 0, you're supposed to walk out between negative r and r, right? And then you rotate a little bit, and then you do negative r and r. And then you do it a little more, and you go negative r and r. And if you only, even if you only rotate halfway, right, you're going to draw the whole thing. So it's another way you could draw that same region. There's not a unique representation of it. There's different ways you could do it. I just want to point that out. Little side note there. All right, got it? Polar rectangle. Let's do it. So I'm going to do my double integral. I think I'm just going to go straight to it. Double integral. Hey, we were only doing the top half, weren't we? So let's go ahead and throw 2 out in front right now because I want to double this answer. And I want to go from 0 to 2 pi. I want to go from 0 to capital R. And then I want the top function minus the bottom function, right? Top minus bottom. The top function's this, but we're going to play that same game we played a little while ago. We're going to turn this into a minus little r squared, right? So it'll be capital R squared minus little r squared underneath the root. Minus the bottom function, which was just 0. And then, because we went to polar, r, and then dr d theta. Who wants to volunteer to forget the r on the final exam? Anyone here want to? Thank you very much. Got a second? Anyone else? Who's going to forget the r in the final? All right, all right. Yeah, all right. There we go. That is the integral. Any questions on that? We're not done. I'm going to take this all the way. We want to prove that the volume is 4/3 pi r cubed, all right? So remember, capital R here is a constant, right? Capital R is a constant. So I'm going to start doing my integration. 2 integral 0 to 2 pi. Here comes the inner integral. I need to go find the antiderivative of this. So I need to go do that. I should do that on the side maybe for you. Let me do it on the side. I'll do it right down here. I want to do the integral. Let's just do the indefinite integral first, and then I'll come back in and put my limits of integration. All right, I'm going to do a basic u sub. U is capital R squared minus little r squared. The derivative of that is negative 2 little r d little r, right, because this is a constant. And in my integral, I have an rdr. Here I have rdr. I need to get rid of that negative 2, so I scale everything, divide both sides by negative 2. We've got this. So I replace rdr with this. I replace the r squared minus little r squared with u. And so this becomes negative 1/2, comes out as the integral. And then I'll have square root of u and then du. And then the antiderivative of the square root of u is going to be 2/3 u to the 3/2. I still had a negative 1/2 in front. 2 times 3 u to the 3/2 plus a constant. Sorry, that's... That all ring a bell? Yeah? This, yeah. No, we need assistance. We want to talk about that more or no? So that, I think I'm going to plug in now here. This is my antiderivative. The 2's go away. So negative 1/3 u, right? U to the 3/2. U was what? Capital R squared minus little r squared. So capital R squared minus little r squared, 3/2. That's the antiderivative, but we want to evaluate it at the two values of what variable? R. Little r, big R?
Little r.
Little r equals 0, little r equals big R. And then d theta. right? We're going from little r is 0 to little r is big R.
We can pull the coefficient out.
This one right here, you want to pull that out now? We can. Yeah, I can bring that out front. So this now becomes negative 2/3 integral 0 to 2 pi. There's nothing wrong with pulling that out now. So okay, now I have two things, right? I have to plug in and subtract. And I still have a d theta at the end of this. All right, what happens when we plug capital R into little r? It's 0, right? It's capital R squared minus capital R squared, which is 0. It just kills that off, okay? And then when we plug in 0 for little r, we don't get 0 this time. We get just that, right? So that'll be, we pulled the third out, right? I already pulled that out, so just ignore that for now. So if I plug 0 in there, I get capital R squared to the 3 halves, right? To the 3 halves, which will turn out to be r cubed. Ooh, there's an r cubed. Our answer should have an r cubed, shouldn't it? Clean this up. Negative 2/3 integral 0 to 2 pi. Wait, that's a minus, isn't it, right here? Because that's 0, then take away this. Can I bring that negative out and just make that a plus? Okay, let's do that. Let's get rid of that. And then this is just r to the 3rd d theta, because, again, you take that, multiply those two together, 2 times 3 halves, the 2's cancel, you just get 3. And now you're integrating a constant, aren't you? The antiderivative of this constant is the constant itself times the variable theta, but from the two limits of integration, theta is 0 to theta is 2 pi. This never gets old. This is 2/3 capital R cubed. When we plug in 2 pi for theta, we get 2 pi. And then we take all that, and now we plug in 0 for theta, and that kills everything, doesn't it? And that's the answer, 4/3 pi R cubed. Right? Because, yeah, obviously, yes. All right, so we just proved that the volume of a sphere is 4/3 pi R cubed. That concludes this section on polar coordinates. And now we're going to do a section on applications. Y'all doing all right?
No.
No? Tired?
Seems like black magic now.
Like what?
Black magic.
All right, what we're going to do now is some applications of this. So I was looking for something earlier today, I couldn't find it.